Hey everybody! For today, we're going to be talking about sensitivity testing, and specifically sensitivity testing using antibiotics and disinfectants and antiseptics. And we're really just going to talk about both of those together because normally whenever we run these labs, the techniques are basically the same and we use the same materials mostly. So it's just easier to make one video about it rather than making two. But really, when we're talking about sensitivity testing, what we're saying here is that we have an agent, again, whether that's an antibiotic, disinfectant, or antiseptic, and we want to know how well does my agent basically kill a specific type of microbe. So that's kind of the basis of this sensitivity testing. And there are three basic ways that we can go about doing sensitivity testing. There's a tube dilution test, a Kirby-Bauer test, and an e-test. And while we're going to focus on the Kirby-Bauer test for our video here, you do need to know how the tube dilution test and the e-test works as well. So with that in mind, again, I'm going to post another video that kind of goes through and discusses those other procedures. So make sure you look at those for your lab quiz. But kind of with that in mind, again, let's talk about the Kirby-Bauer test and the way that the Kirby-Bauer test works. So the Kirby-Bauer test is a sensitivity testing mechanism or a method where that we utilize a plate with multiple antibiotic discs on it. And the main idea with the Kirby-Bauer test is basically just to get a view of what works. So we want to test a whole bunch of different antibiotics or disinfectants and antiseptics, so a bunch of different agents. And we're trying to see how well do these work against our specific bacteria that we're looking at. And from that point, we can then try and do further testing on it. So we're just kind of getting a view of what works, basically, is the basis of the Kirby-Bauer test. So with that in mind, let's talk about what materials that you would need in order to actually perform a Kirby-Bauer test. So you are going to need a plate with what we call Mueller-Hinton 2-auger on it. And they do come kind of in two versions. We can have our standard size plates, or we might have these sort of giant plates, again, way bigger. And we tend to like to prefer to use the bigger plates. The main thing here is that while we can do it on the small plates, no problem, you have a bit more room on the bigger plates, so you can put more discs on it. And the more discs you put on it, the more things you're testing at one point, so your testing is going to go faster, basically. Now, when it comes to the Mueller-Hinton 2-auger, this is basically very similar to our standard growth medium that we've been using. So it doesn't have any selective components, there's no differential components, and there's no pH indicator in it. None of that stuff is in there, it's just there to grow our microbes. But the way that it is different is that it actually allows these different types of agents to basically fuse into the media and disperse throughout it. So what ends up happening is that we're going to put, again, our little discs on it that has these different antibiotics, disinfectants, and antiseptics, and it sort of fuses into the media and creates kind of a ring around the disc where this agent now is. And because of that, again, it's just a little bit better of a medium to do this sensitivity testing with. You can use standard growth medium, but the Mueller-Hinton 2-auger is the most preferred way to do it. So, long story short, you need a Mueller-Hinton 2 plate, preferably the big one. Another thing that you're going to need are basically all the materials that you would need in order to do a lawn procedure. So we are going to do a lawn on this, so you're going to need the stuff to do a lawn procedure. Again, I would suggest doing that with a cotton swab, but you can do it with a lube if you want to. The next thing you're going to need are then everything to do a disc application technique. So if that is an antibiotic disc application, then you're going to use all the materials for that. If it's a disinfectant or antiseptic one, you would then go ahead and need all the materials for a sterile disc application technique. So depending on which one we're doing, probably going to be doing both, you're going to go ahead and need those specific materials for those items. Now, you're also going to need your sample, of course, so that you can actually transfer those materials or transfer that sample onto the plate. And then the last thing you're going to need is going to be a ruler. And we'll kind of talk more about where we're going to be using the ruler when we get into the scoring part of it. So in terms of the procedure that we use in order to perform the Kirby-Bauer test, it is pretty straightforward, but it is a very repetitive technique. So you're going to start out basically labeling everything, and this is very important. We have already talked about how we label everything in class, but when it comes to this procedure right here, there are many ways that we can basically miss labels, and if we do that, we won't even know what's on the plate or what it is that we're testing. So with that in mind, again, if we look at something like this one here, this was one that I made, and basically what we're looking at here again is that I have my standard initials on here, name, so my initials, I have Micrococcus luteus, that's what I put on there, the date that I did it, it's a Mueller-Hinton 2 plate, it was inoculated at 25 degrees Celsius. So again, those are our 5 standard items that we should have on a plate. And then everything that you see around here, along the edge, that's everything that I put on the specific discs that I put on the plate. And it's very important, again, that we put all of those items on there as well, because if you just plop all your discs on there and then we come back to next class, we have no clue what's on the discs. So we need to make sure, again, that we add those specific values on there as well. What ended up happening for one student, which is what we're looking at here, is that they forgot something. So let's say, to not give any indicators or identifiers for this student right here, let's say that this was made by Gabby Brown, and I want you to tell me what's missing on this one here that's going to make it problematic for us to determine what it is that we're looking at next class. All right, there is one way that you can be saved on the antibiotic side of things, and that is basically that every antibiotic disc that we use has a little code on it, so kind of like in the image here. And that little code can basically go into the big tables that we're going to talk about here in a little bit, and it'll basically indicate with that specific code what antibiotic disc it is that you're looking at. When it comes to the disinfectant and antiseptic side of things, again, these are sterile discs, so there are no codes on those. If you don't put down which type of disinfectant or antiseptic that you used, we have no clue what you tested and basically just wasted our time at that point. So make sure that you label everything appropriately. So step 1, label. Step 2, do a lawn plate. So you're basically just going to use your standard lawn technique in order to put your sample all over the plate. And then after that, you're going to do your sterile disc application or your antibiotic disc application, depending on which lab it is that you're doing. And at this point here again, you're just going to perform that technique for however many discs it is that we're going to be putting on the plate. Generally, when we use a small plate, we'll do 4 discs, and then when we do these bigger plates, again, we will do 6 discs because we have more room. So pretty straightforward again. Label everything, do the lawn technique, do your disc transfer technique, and then we're going to put them in the incubator in order to allow them to grow and incubate again for that 48 to a week or so, 48 hours to a week or so. And a big thing here, you have to do the lawn before you do your sterile disc application. If you do the sterile disc application, just the disc application first, when you go to the lawn technique, you're going to knock all the discs off of the plate. So make sure you do the lawn technique first, then do the disc application technique. If not, you're going to mess up the experiment. All right, but kind of with that out of the way, let's go ahead and move to the scoring part of this lab and the way that we actually score our plates. And this is where our ruler is going to come into play. So again, on the rulers, we want to measure in millimeters. So on the metric side, which is the one at the top, you can kind of see how there's all the little numbers. It goes from basically 0 all the way to 15. You can't really see the 15. Well, kind of. Anyways, it goes from 0 to 15. And each of those little numbers represents a centimeter. Each centimeter has 10 millimeters in it. So what we're actually measuring with are going to be those tiny little, I don't know if I can get the focus here. It's going to be those tiny little lines in between, again, our numbers. So each of these tiny little lines up here is 1 millimeter, and that's what we're going to be measuring in order to basically get what we call a zone of inhibition. So when we're looking at our plates, if we're looking at, I guess let's do this one here, we have to measure the zone of inhibition, which is the clearing. So when we're looking at something like this right here, this clearing of growth is what we call the zone of inhibition, and that's what we want to measure. And in order to measure that again, I'm just going to take my ruler, I'm going to put it across, and I want to measure out the full diameter of that. So all the way from one end to the other, looks like that's coming out to be just about 28 or something like that. All right, so we got our 2, that's our 3, so a little bit before 28, 29, something like that. It's a bit hard to see holding it that way. But that would be my zone of inhibition measurement for this one right here. And while again, that might seem kind of simple to do, just measure again how big the diameter is across your specific zone of inhibition, it does take a while to do for all of them. There are a couple, and I guess there are a couple ways that this can be a little bit tricky. So if we're looking at something like this one, let me see if I can get it into view here. All right, so this hydrogen peroxide up here, what you can kind of see is how there is a defined clearing, then there's one that's a bit less shaded, and then there's even a third ring that we have that's a little bit more darkly colored. When we do our measurements, we would have to go all the way to the edge of the third ring. And that's because basically what's happening here is that when we first put this on here, it was effective all the way out to that third ring. And then over time, either the specific agent is diffusing out of the plate or the microbes are neutralizing it. And because of that, it's basically making a smaller and smaller area where that our agent is effective. So we want to get the full view, that's what we're looking for. So we have to go all the way to that outer ring. So again, if I were to sort of measure that out, so kind of like that there again, I would be going all the way again kind of to that outer ring, so it would be about 50 as I'm going across. So that's one way that this can be a little bit tricky to look at. Another way that it can be a little bit tricky is that if we have something like this. So in this case here again, now we have colonies that are growing inside of the zone of inhibition. And we still want to again go all the way to the edge whenever we calculate out our diameter. So disregard the ones that are growing on the inside of there. Again, that's just because the area is becoming weaker and our microbes are becoming more able to live in those environments. Another thing that we can see, where was that at? Are sort of these faded out areas. No, not that one. This one, there we go. So this one here, again, it's kind of hard to see, but you can see how there is a defined ring. That's kind of what we're looking for. And even though, again, it's starting to grow into it, we would still count that entire ring when we're doing our measurements. To show, again, one that is very, very small, if we're looking at our cleaner up here, again, you can see still a nice defined ring, but it is just very tiny, but we would still count that, again, as a zone of inhibition. And you can disregard basically the disc itself. You just go all the way across to get the diameter. So let me show you one that does not have a zone of inhibition around it, which could be kind of like this one here, or penicillin. So this penicillin right here, again, there's no zone of inhibition around it. Another one could be like the Vanco. The Vanco didn't really do anything either. So those would just be considered zeros. We would just write those down as zeros basically in terms of doing our data. All right, last thing to talk about when we're talking about scoring these specific items here, and that's gonna be, it didn't happen with my plates, but what you can end up getting is that if your sample for some reason is either so powerful or you had two powerful kind of next to each other, what you can end up with is that you don't have a full diameter across. You only have a portion of that circle that you're looking at. So again, if we kind of go back to this one here, let's assume that for some reason, again, these two worked really well together and it sort of cuts off right here instead. Now I can't go all the way across, and I still want to, get a good measurement. So remember, diameter is simply a radius multiplied by 2. So if I want to calculate out, again, my diameter, but I don't have a full diameter, I can just take my ruler, put it again about halfway across my disc, and then I can go out, see if I can put my hand up, there we go, And now what I would do is I would just measure down my radius, that's about 25, and then I would just multiply 25 by 2 to get the 50 that I got when I went across the full diameter. All right, that's enough about all the different ways that we can basically look at and score our specific tests. The next thing we have to talk about is then going to be how do we actually interpret all of this. So here's a data table. This is basically the data that we got for the 4 organisms that we tested in class against the 6 different antibiotics that we used. And when we have all this different data, there's a couple different ways that we can basically look at it and interpret it. So first thing first, and this is where that our antibiotic sensitivity tables come into place. Again, we're going to look at the antibiotic data first, and then we'll get into the disinfectant and antiseptic data. The first thing that we would want to look at is basically find each of the different antibiotic discs that we have, and then we have to look at these specific ranges for whether or not our organisms are resistant to it, meaning that they were not killed by the antibiotic and we can't use it in a medical setting. If they were intermediate meaning that it somewhat kills it, so it's kind of like a backup in medicine. And then whether or not they were susceptible, meaning that it kills that organism well, and it would be a good candidate, again, for some sort of medical application. So when we're looking again at these specific items in our table, again, we kind of have our list, which was our resistant, intermediate, and susceptible, and then we find our specific antibiotic in this list, and then we can look at these different ranges. So if we start out looking at, again, our penicillin. Penicillin has a range of saying that anything that is a diameter of 14 or less, so equal to 14 or less, that makes it resistant, and anything that is 15 or greater is now susceptible. Considering that all of ours had a 0 on the penicillin side, they were all resistant to penicillin. It didn't work against any of the bacteria that we had. It also just happened that this one didn't have an intermediate range, but the next one will. So penicillin was pretty easy to score, basically, or interpret. Again, they were all resistant. If we go to chloramphenicol, which is our next one, now our range is anything that is 12 or less, that's going to be resistant. 13 between 17, in terms of, again, our zone of inhibition, that's going to be intermediate. And then anything 18 or higher is going to be susceptible. So as we're looking down through our list, we can tell that Bacillus cereus, having a 13 score, would be intermediate. Micrococcus luteus, having a 10 score, is resistant. Pseudomonas aeruginosa, having a 19 score, is susceptible. And then E. coli, having a 10 score, again, is resistant. So that would be the scores that we would give for that one there. And then we move on to the next one, kanamycin. So 13 or less is resistant, 14 through 17 is intermediate, greater than or 18 or greater is going to be susceptible. So what we're looking at here again is Bacillus cereus, Micrococcus luteus, and E. coli. They're all over 18, so they're all susceptible. And then Pseudomonas had a 0, so it was resistant. We would then continue on with the next one and the next one and the next one. And just to kind of speed this up a little bit, here are all the scores. Like here's the ranges and the scores that we would get for those ones there. And now that we've basically indicated which ones are resistant, which ones are intermediate, and which ones are susceptible, it now allows us to interpret the data a little bit more. So first of all, let's go ahead and break down our organisms into which ones are gram-positives and which ones are gram-negatives. And the big thing here is that gram-negatives tend to be a little bit more powerful or a little bit more resistant compared to our gram-positive organisms. So with that in mind, we're going to go through and we're basically going to give our organisms kind of an arbitrary score based off of these resistance, intermediate, and susceptibility that they have. So we're going to look at this from the bacteria side of things. So when we're talking about the bacteria side, if you're resistant, it means you're strong, so you get a +1 point, basically. If you're intermediate, it means you're somewhat weak, so you get 0 points. And if you're susceptible, you're going to get a -1 point because you are so weak that you were killed. So next thing what we would do is that we would basically go through and we would look at something again like our Bacillus cereus, and we would count out, okay, how many resistance do we have? So we have 3 resistant ones. Okay, so that gives us a +3 score. We have 2 susceptibles, so we have to subtract 2. So 3 minus 2 is 1, and then our 1 intermediate is a -0. So at the end of it all, we get a +1 score for Bacillus cereus. The next thing we then do is go to Micrococcus luteus. Here we have 4 resistant, so we have a +4 score, 2 susceptible, -2, so we get a score of 2. We then do it for Pseudomonas and E. coli as well, and both of those ended up with a +2 score as well. And with that information, what we can basically say is that in terms of which one of our bacteria is the strongest, well, it looks like Pseudomonas, E. coli, and Micrococcus kind of tied in first place because they had a +2 score. And then our Bacillus had a +1 score, so it's the weakest in terms of antibiotic sensitivity. And that's one way that we can go ahead and interpret our data. The next way that we can do it is doing it based off of the zones of inhibition and how much our different organisms were inhibited. So what we're going to do now is that I'm basically going to go across with my Bacillus cereus, and I'm going to add up all the numbers that I have to get a total score. And then I'm going to do that for the other organisms as well. And in this case here again, we're looking at this from the bacteria side. So the smaller the zone of inhibition, right? The smaller that zone of inhibition is, the stronger the bacterium is because it grew more around our specific agent. So what we're looking for here is that whichever bacterium has the smallest number is going to be the strongest bacteria. And with the data that we got, it looks like Pseudomonas was the strongest, number 2 was Micrococcus luteus, number 3 was E. coli, and then lastly, my Bacillus cereus was number 4. So it kind of helps go along a little bit with the data that we got before. The last way that we're then going to interpret this from the bacteria side is basically by looking at, again, gram-positives versus gram-negatives. So I'm going to take the 2 numbers that I got for my gram-positives and add them together. Then I'm going to get the 2 numbers that I got for my gram-negatives and add those together. Then I'm going to look at, again, which one is the smallest. And it comes out again to be that my gram-negatives had a smaller zone of inhibition altogether compared to the gram-positive. And again, that kind of goes along with the fact that gram-negatives are a bit stronger than gram-positive organisms. All right, that's the way that we would go ahead and interpret the data from the bacteria side. The next way that we're going to interpret our data is from the antibiotic side. So now what I'm going to do is that I'm going to go through and I'm going to add up all my penicillin numbers, all of my chloramphenicol, all of my kanamycin, all my gentamicin. I'm basically going to get all these total volumes at the bottom. And what we can look at here then is that now we're looking at this from the antibiotic side. The better the antibiotic, the bigger the zone of inhibition, because the more it killed the microbe. So in this case here again, what I'm looking at is, if I look at all of my numbers, it looks like gentamicin came out on top with the highest number, so that was my strongest antibiotic. Then it was kanamycin, then it was chloramphenicol, and then basically penicillin, vancomycin, and erythromycin, they all tied for last place because they didn't do anything against our specific organisms. So those are all the different ways that we can basically interpret the data that we have for our antibiotic sensitivity testing. And just one note on using the big tables that we have, what you can end up with is that there's multiple numbers, kind of like in this example here. And for our class, we are either going to use a Staphylococcus, and if it is not a Staphylococcus species, you can consider it to be an Enterobacteria species. So with that in mind, again, basically, if it indicates that it's a staph species, use the staph numbers. If it's not a staph species, use the other numbers, the Enterobacteria group, basically. And that will just make it nice and consistent across the board in terms of how we interpret the specific data that we have. All right. That should basically be everything that I need to talk about in terms of the antibiotic side of things. So let's move on to the disinfectant and antiseptic side of things. So similar thing here again, here's the data table that we have. We basically looked at bleach, our lab bench cleaner that we use, Lysol, like a toilet bowl cleaner, hydrogen peroxide, Dawn, like a soap that you use to wash off dishes, and then some Listerine. And we're going to basically, again, kind of look at this in a similar way. There aren't any big tables that we can use to reference for antiseptics and disinfectants, so it's a little bit easier to interpret the data. So we're going to start out, again, basically just by looking at which one is the strongest bacterium. And by doing that, I'm going to take my Bacillus cereus all the way across, get my total number, go to my Micrococcus luteus, again, all the way across, get my total number, do that for all of them. And then I'm just going to look at here, which one of these has the smallest number. That would be my strongest microbe, again, because it had the least amount of inhibition. And in this case here, it looks like my Bacillus cereus was the strongest one against antiseptics and disinfectants. Then it would be my Pseudomonas, then my E. coli, and then my Micrococcus last. And that would be the way that I would score those. Now let's compare them again, gram-positive versus gram-negative. So if I take my 2 gram-positive together, my 2 gram-negatives together, it looks like my gram-negatives still come out lower than the gram-positive. And again, those gram-negatives seem to be a little bit stronger than my gram-positive organisms. The last thing we're then going to do is now we're going to look at this from the agent side of things. So I would go through, I would take all of my bleach numbers, put them together, all of my cleaner numbers, all of my Lysol, so on and so forth. And now I can look at all my total numbers at the bottom and basically say which one of these is going to be, the biggest number, because now we're looking for bigger, meaning more inhibition, meaning our agent worked better. So here it looks like hydrogen peroxide came out on top, then our Lysol, then bleach. Let's see where we're at then Listerine, then Dawn, and then our lab bench cleaner. Makes you wonder about the lab bench cleaner coming out last, but guess we'll worry about that later. So that would basically, again, indicate to us which one of these is the best agent, again, to basically clean our environment. And then lastly, the way that we can look at this is breaking this down based off of disinfectants versus antiseptics. So what's going to happen here again is that now I'm going to take my 3 disinfectants and add those numbers together, and I'm going to take my 3 antiseptics and add those numbers together and look at which ones came out on top. And with the numbers that we got, they were very, very close. Again, they were off by 2 points. So in this sense here, again, they're basically the same in terms of strength. The antiseptics, again, did come out a little bit on top, but really not any noticeable amount. So depending, of course, on which specific type of cleaner that you're using, which disinfectants, which antiseptics, you might get varied results. And again, this is where the data can be a little bit difficult to interpret, again, because it really is depending on the specific items that are used. But really, again, that kind of covers the way that we interpret the antiseptic and disinfectant side of things. So when it comes to your quiz online, what you're going to have is you're basically going to have like a mock experiment, like you did this in class, and you're going to have all this data. You'll have to do all these calculations and score everything the way that we did it, and you'll have some of these tables for the antibiotic side of things to basically go through and look at those specific scores. So kind of with that in mind, again, you're going to have this mock experiment. You're going to be going through and doing all these interpretations yourself and the way that that sort of works out. So just kind of, again, be aware of the way that we interpret things and look at all these different items. Hey, everybody. After going through and making the video, I realized there were a few things that I forgot to mention in the original video, so I'm just going to mention them real fast here. The first one was all the way back when we talked about the sample at this point in the video. And what I forgot to mention is that whenever we do this sensitivity testing, we actually use what we call the McFarland standard in order to determine what type of sample is a good candidate for basically being used for sensitivity testing. And the big thing here is that the McFarland standard, or the scale that we use, is a measure of turbidity, and we always want to use what we call a 0.5 McFarland standard tube. And the big thing here is that if you have a tube that is very, very turbid compared to one that is not very turbid, there's generally more bacteria in the very turbid tube compared to the slightly turbid tube. And because of that, the more bacteria you put on your plate, the smaller your zones of inhibition are going to be compared to the one with less bacteria in it. So with that in mind, again, if we're only looking at trying to determine the effectiveness of the disc itself and that antibiotic that is on it, or the disinfectant or antiseptic, we have to make sure that the amount of bacteria that we put on there is the same between all of our samples. If not, we're basically having multiple different variables in our experiment. So the 0.5 McFarland standard basically correlates to about 1.5 to times 10 to the power of 8th colony forming units, or CFUs, per mLs. So again, that's one thing that I forgot to mention. We have to keep this standard so that we're only testing the specific agent that we're testing, and we're not basically changing the amount of bacteria that we're putting on our plate. The other thing that I forgot to mention was in the scoring part of this when we were looking at the antibiotics and the way that we score them. So in the video, I just go through and I just directly score them based on their zone of inhibition numbers, and that was a little bit different from the way that we scored the bacteria. With the bacteria, again, we first gave them that arbitrary score based off of their resistances, intermediates, and susceptibility, and then we looked at the numbers. So let's go ahead and basically talk about doing that part with the antibiotics as well. And when it comes to this from the antibiotic side, so I guess let's get our table in here real quick. When it comes to this from the antibiotic side, we're going to flip the scale. So now, when we're looking at it from an antibiotic perspective, if our organism is resistant, it means that our antibiotic is weak. So now it gets a -1 point. If it's intermediate, it's still a 0 point. And if the organism is susceptible, we're going to give it a +1 point because the antibiotic is strong. So looking at that and basically looking at our resistances, intermediates, and susceptibles for our different antibiotics that we have, if we start out again with penicillin, penicillin was all resistant, so it gets a score of -4. Same thing is going to happen for vanco and erythro because those were all resistant as well. So a -4 score again because we just had 4 minuses. When we look at something like chloramphenicol, we have 1 susceptible, so that starts us out as a +1. We have 2 resistances, so we have to subtract 2, and we get to -1. And then we have 1 intermediate again, which is a -0, so the final score is a -1. Looking at kanamycin, we start out with 3 susceptibles, so that's a +3. 1 resistance, again, we take away 1, so now we have a score of 2. And then we have gentamicin, which was all susceptible, so it has a score of +4. And again, that's one way that we generally start out, looking at these sensitivity items. And in that way, again, if we have any of these that come up with the same numbers, we can then switch again to looking at the specific zone of inhibition numbers that we have in order to determine which one was the strongest. But looking at this data again, it basically comes up the same as what we did when we just looked at the numbers. So gentamicin had the highest score based off of just susceptibility, and it also had the highest zone of inhibition. The next best one would then be kanamycin. Both of those scores are second in line, and then chloramphenicol had the 3rd highest score for both of our values. And then basically penicillin, vanco, and erythro all come out as number 4 based on, again, having a -4 score and having a 0 in terms of zone of inhibitions. But at this point again, I think I am now done with everything that we need to talk about this lab.